Hello, everyone. It is February 18th at noon, and I am just logging on to give you guys an intro to the lab that I announced last week, but this week is actually when it's supposed to be done. Of course, you could have completely done it already. There was a video in week five. I've now made that week five, and six since we only did, since I gave you that week off, that was week five. Uh, Basically you could have done that in week five, but you can also do it now in week six. So I just made that one module instead of being week five from such and such a date. I made it week five and six from whatever that date was. I can't remember. But up until now, it'll be March 3rd. And then, of course, the lab is due by 11:59 on March 4th. So this is the linear graphing one lab, and I'm here to give you a little intro to it. And of course, I always have my office hour, which starts around 12:30, 12:35, because it normally takes me about 35 minutes to uh, get through explaining what they're going to do for lab. So that is still an office hour. Remember, everybody should have access to that through the invitations, the Zoom invitations that I posted on each of my courses uh, Canvas page. So let me go ahead and share my screen so we can discuss the actual lab that we're going to be doing. I got to make sure I get it on the right lab. There it is. Okay, so now I'm going to share my screen, and that should show up as the lab we're going to do, and then I'll also show you the addendum to it, which is how we make it into a online lab. Again, this isn't the best quality lab that I would prefer you guys to do, and a lot of places aren't accepting these online labs, except in some cases as electives. It all depends from place to place, but either way, this is what we're doing. It's called Lab 5 Linear Graphing 1, which you actually are only treating two things. That's an Atwood machine and a very special way of doing an Atwood machine, by the way, and a ball on the carpet. So in the ball on the carpet, of course, you'll be putting two meter sticks together, or actually just be using the data from putting two meter sticks together. But you put two meter sticks together with tape, that makes a little channel that a ball could roll down. You roll the ball down the channel. It then goes, depending on how far up the uh, ramp that was made out of the two meter sticks, depending on how far up you were up that ramp, when you release the ball, it's going to roll a certain distance along the carpet, which is sort of like a brutal friction type force, except it's not even really a friction force in this typical sense because it's way less uniform. So, anyways, as it says, this lab required a metric ruler, i.e., meters, centimeters, and that sort of thing. A Pentium computer, Excel spreadsheet, two meter sticks, ball, carpet strip, Logger Pro software. We do have the Logger Pro software, and you are able to actually download that. That was, I believe, in the last week's addendum that I passed out as well, but it'll be here still. So, you also had rod clamps and stuff like that. Not really that much important because, as I said, you're doing this at home. So, what they want to remind you is that ideally we would like to have a lot of our graphs turn out to be linear. And so when you make some plot of x versus y with x on the horizontal axis and y on the vertical axis, which we normally call y versus x, by the way, I just said it in reverse order because I was thinking about the order of the actual points. So the points, parenthesis x comma y, close parenthesis in two dimensions, those two variables ideally can be related any number of ways. So for instance, you could have y equal, or you could say, y is directly proportional to x. Okay, that's what I call thumbs up, thumbs up. That's why I was doing this. And what that means in terms of y is directly proportional to x, that means if you double x, you're going to double y. Ugh. If you triple x, you're going to triple y. If you quadruple x, you're going to quadruple y, so on and so forth. And that's given as a y is proportional. It's a little looks like a little fish symbol. Also looks a little bit like the lowercase alpha, but it's y proportional to x. To make that an equation, we all learned this in high school algebra one. To make that equation, you say y equals some constant, let it be c or k or whatever, times x. That is a subset of linear functions. Linear functions are of the form y equals some constant times x plus another constant. We normally call those constants m and b, so it'd be y equals mx plus b. But you can tell in comparing y equals mx plus b to y equals kx, the k is playing the role of m and 0 is playing the role of b. So it's a special case of a linear graph. But you could also have y and x squared are directly proportional. So that would mean y and x squared, thumbs up, thumbs up. But in this case, it's a little more odd in that if you double x, you don't double y. You actually take 2 since you doubled it. Since you doubled something, the multiplication factor is 2 and you square that. So 2 squared would be 4. So when you double y directly proportional to x, when you are directly proportional to x squared, excuse me, when you double x in y directly proportional to x squared, you actually quadruple y. If you triple x, you nine-tuple y. If you quadruple x, you 16-tuple it. If you quintuple x, you 25 tuple y. So that's just y equals some constant times x squared. Of course, you know that's a subset of the polynomials y equals ax squared plus bx plus c. But again, that is a possibility. You could also have y and x inversely related. That's what we call thumbs up, thumbs down. And in that case, you have y equals, or y is proportional to 1 over x. And what that means is when x goes up by a factor of 2, y goes down by a factor of 2 or by a factor of 1/2, depending on how you want to think about it. When I say down by a factor of 2, that means division by 2. When I say down by a factor of 1/2, that means multiplication by 1/2, which hopefully you all know that multiplication by 1/2 is the same thing as division by 2. Uh, that's one other type of relationship you could do for y inversely related to x. And it mainly means, like I said, if one goes up, the other's got to go down. But if you had instead of y inversely proportional to x, you had y inversely proportional to x squared, that would still be thumbs up, thumbs down. But in this case, if you doubled x, you'd actually cut y by a fourth. That means you either multiply the original y value that you had before you doubled x, you multiply that by 1/4, or you divide it by 4. Similarly, if you triple it, you're going to divide it by 9. If you quadruple it, you're going to divide it by 16. If you quintuple it, you're going to divide by 25. So those are just some different relationships. And in history of science, we found very odd relationships. For instance, the one that Kepler found was the square of the periods of the orbits of the planets is proportional to the cube of the semi-major axis. So, if you're going back to the time of Kepler inventing his laws of planetary motion or discovering them, however you want to put it, what you would see there is he certainly didn't have access to the tools that we have now as far as doing the best curve fit. But he could still, in principle, do a curve fit quite straightforwardly. At least if it was a straight line curve fit, it would be very, very complicated for him to do a non-linear least squares fit or a non-linear best curve of best fit. So what he ended up doing was he plotted t to various powers. He plotted t being the period. He plotted a, the semi-major axis, to various exponential powers. So you could do, for instance, t squared versus a. You could do t cubed versus a. You could do t versus a squared. You could do t versus a cubed. T versus 1 over a. T versus 1 over a squared. But you could also do t to the negative 2 directly proportional to a, or t to the negative 3 directly proportional to a. Or you could do t to the negative 2 and a to the negative 4. All sorts of weird things like that. And you start to duplicate yourself if you're not careful. But the main thing is you can plot anything on the vertical axis, anything on the horizontal axis. And ideally, what you'd look for if you're trying to do a curve fit that's just a straight line curve fit, you want to find the relationship graphed on the vertical axis and the horizontal axis such that the data points make a straight line. It could be up and to the right, it could be down and to the right, it could be well, it could be level, completely horizontal. It could be vertical, all sorts of stuff like that. But we have very specific physical reasons for getting rid of ideas like directly horizontal or vertical, especially. There's a really big, a good reason for that. But either way, if you find the combination of variables that represent x to raise to some power and variables that represent y raised to some power, and those particular variables raised to those powers give you a linear assortment of data points, then you can just sort of eye it. And what you try to do is you draw a line of best fit that goes sort of equal distance from all the points. That's sort of the ideal scenario. If all the points were equally weighted, then you'd expect all of them to be equally close to the graph that you chose. Or you could just do it brute force, which is sort of what the linear regression does. In that case, if I remember correctly, I believe what they did is they take a hypothetical y equals mx plus b, with y being whatever you plotted on the vertical axis. It could be t squared, and then on the horizontal axis, that could be a cubed, for instance. That's what Kepler did. When you did that, then it's just y equals mx plus b, and with that, what you could do is say, okay, I'm choosing a particular m and a b because it looks like it fits the lines pretty well. Then you drop a vertical line from any y, or excuse me, from any point that the data gave you down to the line that you're graphing. And if it's a data point below the line that you're graphing, then you take the distance from that data point up to that line, and you add all those up and figure out some way to minimize that sum. So you're looking for the distance between the vertical distance specifically between a data point and the test y equals mx plus b equation you chose. The least squares linear regression is a method of minimizing that, and it gives you, in some sense, the best answer. Now, that could mean that some of the data points end up hitting right on the line. Some could be very close, some could be a little farther, but the main thing is it did a minimization process. So what you're going to do when you make a graph of your own, specifically, this is a skill that you guys need to do. And even though the linear graphing lab does not require it, doesn't say this, I am requiring this of you, and I'll put in a separate turn-in area for this. I want you to make one of your graphs take up as much of a page of graph paper as possible. So, and I would say probably you've got to hit at least the 75% of the area of the page for me to give you a positive grade on that. Okay. So what that means is you might have to not physically be able to show the origin either. For instance, you're going to say, what's my biggest range of values? Is that the variable that I put on the y-axis, or is that the variable that I put on the x-axis? Whichever one has a biggest y value or x value down to a smallest y value or x value, whichever has a largest number there. In other words, you take the big number minus the small number, the very biggest, let's say in terms of y, let's say you take the biggest y minus the smallest y, that gives you a numerical value of the range. Then you take the biggest x and the biggest y, or excuse me, the biggest x and the smallest x, and again you do a subtraction, big X minus small x. Whichever one of those have the largest number when you do that subtraction, one's called the range, the other one's called the domain, I guess. But when you do that, the one with the biggest of those numbers, either the domain or the range, that should be plotted on the 11-inch side of the graph paper, whereas the 8.5 side should be the one with the smallest difference between large value and small value. Okay, so that decides whether you're going to graph it in landscape or portrait mode, in terms of what you're used to using Microsoft Word and stuff like that. Now, the next thing you'd have to do after finding out what that highest y and that lowest y is, and that highest x and that lowest x, which again, remember that y could be t squared, that x could be a cubed, or any other variables. But the main thing is, once you decided on what made that straight line, you're going to compare the largest of those variables minus the smallest of those variables, and the one that has a bigger difference that should be plotted on the 11 inch side of the graphing paper. Now, you then count the number of squares, for instance, on the graphing paper. Say you've got, 52 squares, and you know that the range is, let's say, 20 for the y, and let's say that is the biggest. If that's the case, if the range for the y was the bigger between the range and domain, then you would put it on the 11 inch part of the page. In other words, in portrait mode, the y-axis would be vertical. And with it in that portrait mode, you then say, okay, well, this difference, which let's pretend like it was 20, this difference has to be shown from, the smallest number up a distance of 20. I've got 52 spaces to fit that in, so let's figure out how big of a space I can make one change in those numbers. So we make up a scale so that basically my lowest y value will be very, very close to the very bottom of the 11-inch side of the page, and my largest y value would be very, very close to the top of the 11-inch side of my page. Again, like I said, the ideal scenario is bare minimum 75% of the page will be taken. Now, that's a scale for just the vertical. You also have to make a scale for the horizontal, and the two don't have to be equal. Okay. In fact, it's perfectly fine for them not to be equal. But when you do that, then you got to actually take the time to figure out what the X and Y points are on the graph that you make. So if, for instance, if the range, which in X values is what we call the domain. So if you took the biggest X minus the smallest X, and you got, instead of 20, since it was the smallest one, say you got 15. Well, if the paper was 30 rectangles or 30 squares wide, you try to figure out what is the biggest amount of squares I can give for 1 unit change in the x-axis, so that you basically have the smallest x value in the bottom left corner of the 8.5 by 11 page, and then the largest x value would be in the bottom right corner of the 8.5 by 11 graph paper page. Again, you want them both very close to the end. I'm thinking like two or maybe three at most squares from the top, two or maybe three or at most squares from the left, two or maybe three squares below the bottom, and then two or three squares to the right of or to the edge of the page from the graph. So that's really what you're shooting for. I need you all to work that out one good time. So you're going to have to make an entirely separate graph. I want to know the data you're plotting. You can use the data here, or you can use some of the data that was given to you in last week's lab. Doesn't matter. Just find one that you like and that you can deal with, and you're going to turn in that whole page of the graph that you fit to the maximum size of the page that you could fit, and also a second page that has the data that you used, and you're going to actually find the line of best fit by eyeing it. Ideally, the best way would be using a clear ruler so that you could actually, or straight edge, so that you could actually lay it down and see how the edge of the ruler fits amongst all the points. If the ruler wasn't clear, it would be hard to see what you're doing with any of the points that would be under the ruler. So the clear ruler would be better. Another option, of course, is you could take some really, really thin paper. For instance, we used to use typing paper. You can almost see through that. If you make your dots on your graph dark enough, you could easily lay a thin sheet of paper over top of it and see through it to figure out where the edge of that thin sheet of paper should be. Because you can now see the data points that are under the paper as well as the ones that are above that are not under the paper. And then you could just make lay out a ruler parallel to that edge and then draw the line with that straight edge, and that would be your line of best fit. Once you have that line of best fit, you have to take 2 points off the line. Again, that means you've got to use your scale that you use for the y-axis to figure out what your point is for each of the points, and then you've got to use your scale that you made up for the x-axis to figure out what your x point is for each of those points. And again, that can be a little difficult, but it's just something you got to use your scale for to figure out. Once you do that, once you find the actual real x and y value of 1 point on the line, and obviously you would probably want to look for a place where the actual lines of the graph paper come together and your line just happens to go through one of those. Hopefully there'll be one like that and you will record that X and Y. But even more hopefully is maybe there will be another one that's equally easy to discern exactly what X and Y value they are. So you'll have two X and Y values, X1, Y1, and X2, Y2, and then you can compute what the slope of that would be by Y2 minus Y1 over X2 minus X1. That would be the slope. And then once you have Y equals MX plus B, you now know M, but you don't know B, but you can plug in any X, Y value again from the line, not from the data. You can plug in any specific X and Y value with now that you know that M, and that will allow you to determine the B. And I want you to show me those calculations either on the page with the data or out of the way of the graphs on the graph would be acceptable as well. But I want to know what specifically you deemed the y equals mx plus b equation to be with your curve fit. And ideally, you'd go back and look and you'll realize how good you were compared to the version that Microsoft's Excel did. Okay, so that's a separate assignment that is counting as a whole nother lab. In addition to this lab, I will give you 2 weeks to do this since I really wanted to do it last week, but I didn't put it on the video. So you can have up to 2 weeks to do it. You'll see that listed in the turn-in section. So make sure uh, by Tuesday, 11:59 p.m. of next week, you turn in your lab report for linear graphing 1, and then by Tuesday the following week, which I think is May 4th, uh, at 11:59 p.m., you will need to turn in an actual hand-created graph that takes, as a bare minimum, 75% of the area of the graph paper and doesn't necessarily have to show the origin. And in fact, when you draw the line and if it hits the vertical axis at all, that might be good, but you got to pay attention to exactly where it hit. It's not necessarily, for instance, if it hits at what you've drawn as the origin, that origin isn't necessarily the point 0, 0 if you didn't start the x values at 0 and running to the right and the y values at 0 running upward. So you got to pay attention to that. Now that I've explained all that, and feel free to send me questions. I know I'm explaining stuff uh, by words instead of by writing things down, but I don't see much advantage in writing anything down for you explaining that. Just ask me if you have difficulties. But again, you're supposed to figure out which variable, the thing you're plotting on the y-axis, which we'll call the y variable, but could really mean t to the 1/2 power, or it could mean x to the 3rd power, or whatever. And then you got to find that range and then stretch it as large as you can on the paper. But you also got to do the same thing for the x values, and you got to decide whether you want the what you called the x values plotted on the long edge of the paper, or do you want them plotted on the short edge of the paper. And again, what that depends on is how big the difference is between your largest y value and your smallest y value, and the difference between your largest x value and your smallest x value. The one of those that has the biggest difference between the largest and smallest is the one that should be aligned to the 11-inch length of the paper. So now let me get back to the linear graphing part. As it shows you here, this is a graph of a straight line, it's obvious that it's a straight line. It's also obvious that the points don't sit on it perfectly, but they're pretty close. Like this one, you can tell clearly the center of the dot is not on the line. This one, the center of the dot looks a little bit below the line. Same thing with this one. This one looks like it might be right through the middle or very close, but ideally that's what you want. But also, if you made your graph that small, you're shortchanging yourself because you're not really able to see is it even remotely reasonable for the line to be that thick? Because in fact, those none of those points might actually be touching the line at all. It's just because your dots and your lines are so thick. So that's why we try to make the graphs as big as possible when we're analyzing them by hand. But the main things you're going to do is read this lab. It's going to give you very specific data you can graph. Here's time and speed, for instance, and it lets you graph those. And it tells you to find the slope of the line, the y-intercept. Be sure to take 2 points on the line to find the slope that are not data points. If you actually had a data point that was literally directly on the line of curve fit that you made, it wouldn't be a big problem for you using that data point. It just happened to be a golden BB, as the armed services sometimes talk about lucky shots. So that's okay, even though it's explicitly says not to choose one of your data points. The reason why they say that is they don't want you thinking that the data points represent the data anymore. Once you've made a line of best fit, those data points are sort of just like noise or random results that led to the more conclusive result that your curve fit was. Okay, so you're going to do that for part A, which is velocity versus time. This is a very good candidate because there's a good number of data points. It's a good range. In fact, if you notice the biggest time change, or the let's say the range of values for time, and I said range there, which normally means y-axis, so we could pretend putting the time on the y-axis. What you'd see is the smallest value is 0, the largest value is 4.5, 4.50 minus 0 is 4.50. If you look at the speed, which might be the x variable, you can see in that case the largest value is 23, the smallest value is 8.8. If you subtract 23 minus 8.8, that would be 13, 14.2. So it's clear that the difference between the large speed and the small speed is greater than the difference between the large time and the small time. So you would actually want, whether it's the x-axis or not, you would want the speed plotted on the 11-inch axis, which, again, might be 10 3/4 inches or something like that, but it's a good fraction of the 11 inches. And then you would make the time variable on the 8.5-inch axis of the page, because that range was smaller. Okay. You write the equation there. Again, this is one where you can do it. And I would also recommend, if this is the data that you use to make your hand-drawn graph with your hand-drawn curve fit, you definitely want to run that through Excel as well to get what it actually calculated as the line fit. And when you turn that in, I would like to see both of those results. I want to know exactly what your y equals mx plus b worked out to be, and what y equals mx plus b turned out to be when Excel did it with a extremely awesome mathematical calculation. And hopefully you'll see that you came up pretty close. If you did come up pretty close, that'll be great. If you didn't come up very close, that'd be okay too, unless you just didn't come up close because you screwed up. If you made a mistake in making it and that made you not get a nice curve fit, like you didn't apply your scale and figuring out what your points are or something like that, then that would be a marked number of points taken off your document that you turned in. Other than that, I'm not going to, take off points because you didn't make that good of a curve fit. It's just, something you're supposed to be learning at this point, so not necessarily needing to have. All right, now that we've got through explaining part A and referencing back to the hand-drawn graph you have to do, you can carry on and you'll see now plot the same data with the aid of a spreadsheet. That's where you're doing that. So this is where you're using Excel, and that starts at step 4, and then step 5 or actually after step 7, there's a part B where you're doing the ball rolling on the carpet. I have videos of that, data of that as well. There's your data table. If you decide to use this data table, which is perfectly fine, you will have this Microsoft Word document. You can type these numbers in here, but remember your font has to be some color other than black, because you're typing something in. That means I can't tell if what you typed in is necessarily part of the original lab report or lab document that I gave you, or if it's something you included. The way I do figure out what you included versus what you didn't include is specifically seeing font colors that are not black, or seeing handwritten stuff, which obviously is not part of the lab. Okay, so you can do that, print the graph, so on and so forth. Then you're doing the Atwood machine. Now, I mentioned to you what's special about this Atwood machine is that you are going to have a number of difference in masses. So, for instance, you could have, and I'm making these numbers up, they're not necessarily consistent with the numbers that the lab tells you. But if you considered that you were taking, let's say, 500 grams is the total mass on the two hangers, you would always keep that total mass M1 plus M2 equal to 500 grams. So one difference would be 250 and 250. That obviously is a difference of zero. So you'd expect no acceleration on that. And you would put that in as a data point where your difference is plotted, let's say on the horizontal axis, and the actual acceleration is plotted on the vertical axis. We know from the calculation I did in Atwood machine for you online, as well as in my classes, as well as all over my YouTube channel, that the acceleration due to a Atwood machine is M2 minus M1, where M2 is supposed to be the bigger one, M2 minus M1 divided by M2 plus M1, and then all of that times G, the gravitational acceleration. That is the actual acceleration formula. So in principle, you could plot M2 minus M1 in parentheses times G on the horizontal axis, and what that would show you is the variable x would be m2 minus m1 in parentheses times g, and the y variable would just be the acceleration. And you have a very obvious, since m1 plus m2 is a constant, you have a very obvious slope that hopefully you can figure out. If you chose to do m2 minus m1 in kilograms as opposed to newtons, then you'd have a slightly different but obvious slope. I would say it's different by a factor of 9.8, for instance, 9.80. So, anyways, that's what you're going to do. So you'd start off, for instance, with 250 and 250. That could be a zero, but then you could take and say move 10 grams from one of them and put it on the other one. So the 250 on the left, say, now becomes 240, and the 250 on the right now becomes 260. So now the difference is in fact 20, but the sum is still 500, so that's great. And you do another one, maybe carry another 10 milligrams or another 10 grams over, in which case it now becomes, instead of 240 on the left, it becomes 230 on the left, and instead of 260 on the right, it becomes 270 on the right, so on and so forth. When all that's done, you can figure it out, and hopefully you will verify exactly the answers that I got for you on the Atwood machine when I worked it out in symbol form. All right, so here's where you're going to put those masses. You can see M2 minus M1, that's the delta. Again, you might choose to graph that on the horizontal axis, or you might choose to graph M2 minus M1 in parentheses times G on the horizontal axis. If the actual document tells you specifically to do one way or the other, then do that way. That's the kind of thing that I look at just as I go to grade your lab reports. But if it doesn't explicitly say exactly what you do, you have the freedom of making those decisions yourself. But the main thing is you're trying to get it into a linear fit. So you want to make sure if you do M2 minus M1, or if you do M2 minus M1 in parentheses times G, then you want to make sure you try M2 minus M1 to the 2 power, or M2 minus M1 to the 3 power, or if you're using the M2 minus M1 times G, you want to try that to the 1 power, to the 2 power, to the 3 power, to the -1, to the 1/2, all that sort of stuff that could possibly be. You'll probably have a sense of what it should be and won't have to waste much time looking at all the different graphs. But remember the golden or I should say the standard, the gold standard of the graph is the R squared value, and closer that is to one, the more reliable the curve fit is. So when you're doing Excel, it'll spit out not only, well, you have to click on the button to make sure it spits out the equation and the R squared, but it will spit them out if you click that. And when it spits it out, if your value is like 0.9999, that's really great. If your value is like 0.9899, that's great. Not quite as good as the previous one. When it starts getting around 0.95 or 0.94 or something, then it's a little questionable. So hopefully your data is better than that. Anywhere it says print the graph, uh, you don't necessarily have to print it. I'm trying to make you have a lab where you don't have to actually waste any paper to be printed, but you're welcome to. It's just I would prefer that to be have a photo taken of it, maybe a screenshot from the computer, and then it pasted in the appropriate place in the Word document, and then of course that Word document, once it's completely done, is converted to a PDF and turned in. So that's always the standard in all of my labs is if it tells you to print a graph, you don't technically print it. You take a screenshot of it, or if you did it by hand, you take a photograph of it and then insert that into the Word document, or in the case of our assignment, you could just make that a PDF right from the beginning and include the data and the calculations and all that for that other part. It does provide this graph paper, which is not the best graph paper, but you're welcome to use it. The big thing is here, I need a hand-drawn one, so you would have to print that out unless you have your own graph paper. So that's the only part where you have to do anything. So we have exactly one page that you'll need. And to be honest with you, if you're not really careful, or if you're not good about thinking mathematically about stretching things and stuff like that, it might take you a couple different pieces of paper to try it. So I'm aware of that. It's okay, but like I said, we're saving a lot more paper by not turning in lab reports every week, hard and on paper, but rather in electronic form. So anyways, that's it. It does appear I've waited till at least 12:30 and no one else has arrived, so I don't think anybody's coming for office hours. Now that I've talked about this, let's look at what the addendum tells you so I can better relate to you how you're going to implement this lab. So again, if you look down to, you can see where I called it week 5 and 6, February 11th to February 24th. You'll see right here, this is the addendum. I'm clicking on that. And this says, view the video that shows how the data was gathered. You will complete the lab precisely as explained in the lab book, but using the data below for the ball rolling on the carpet and the Atwood machine. Now, in principle, if you had the right equipment, you could, in principle, make an Atwood machine yourself. You wouldn't be able to do it with the nice Lab Pro stuff that we have because that equipment's made specifically for that. But you can still just make your own Atwood machine. You just want a really, really low mass, low friction pulley system to use. And the way you make it a low mass is sometimes you use larger masses. That's probably where the biggest problem would come in with this experiment because you couldn't do that one at home unless you actually had a weight system or a weight set like we use in our labs. But either way, the big deal is here you do have data that we've given you both for the rolling carpet. So what this means is when you allowed the ball to roll down 10 centimeters on the ramp, in one trial, you got 20.8. The second trial, you got 20.8. The third trial, you got 20.8. So you're ultimately going to take the average of these three, which obviously is just 20.8, and that's what you're ultimately going to graph. You do the same thing for the 15, the same thing for the 20. Similarly, the same thing for the Atwood machine. When the difference in mass was 110 grams, you got 1.306 for acceleration. Then another trial, you got 1.296. Then another trial, you got 1.293. You're going to take the average of these three numbers, and that's what you're going to plot as the acceleration with a difference in mass corresponding to 0.110. You're going to do the same thing with the difference in mass being 0.100 and so on and so forth. But that's it. That's literally the whole process. Let me show you what else is here. So we do have the linear graphing, and you can also see that this right here is a link to a video, and this right here is a link to a video as well. So you can actually see the videos of the data being taken here and here, and you can also see a whole video that's an intro to it. Notice this is the password for that video. It's in, if I remember correctly, it's in the Canvas system, so that's why we had to have a password. So make sure you copy that before you click on it, and then you can type it in by just hitting paste if you do a literal copy instead of writing it down by hand. You can write it down by hand, but there's a chance you'll make a mistake. But it's all those little symbols, the 3, the E, the 5, the at, the O, the E, the percent symbol, and the 9. Luckily, all the letters are uppercase, so you can at least rule out the lowercase letters, which cause problems. But anyways, you're all going to turn this in when you're done with this lab report. It's going to be turned in here, but there's also going to be another slot right here that'll be called something like hand-drawn graph or something. So that's going to be where that is, and both of these will be due on March 4th at 11:59 p.m. So it looks like I've now discussed everything. I'm here for the opportunity in case anyone had office hour questions they wanted to answer, but no one showed up for that. So I'm going to go ahead and call it a day. I'm stopping the sharing. Everybody be safe. There is supposed to be a storm coming. It probably will get in the area late in the night tonight and should be rolling by 7 a.m. tomorrow. So stay safe. Pay attention to your TCC emails or text messages. Sign up for that notification that TCC offers, so you'll be the first, one of the first people to know if they do cancel classes. But just pay attention to that, and also looking for an email from me. If we have to miss any days, I'm going to try to make up videos that we can do in lieu of making up the time and stuff like that. So hopefully I'll send you some emails like that. All right, well, that's it. So thanks everybody for coming. Oh, well, thanks nobody for coming. I'm sorry none of you came. But anyways, have a good day. I will see you next time. Bye bye. Bye bye from me and my minion friend. There's my minion friend.